Hello and welcome everyone in this YouTube channel. Today I'm here to discuss about to share my knowledge regarding a Frank Hertz experiment to prove the quantum nature of a substance. Okay, to study the quantum nature of a substance. This is a Frank Hertz experiment. Today we'll see how to set up this experiment, what is the internal circuit of this experiment, and how does this experiment work, and how can we show that it supports the study of quantum nature of substance. Today in this um, sitting, okay, in this study time period, we are going to learn about these topics. Okay. This is the experiment setup, okay, which we use in our lab. I will tell you how to operate this experiment. Okay, Frank Hertz experiment to study the quantum nature of substance. Okay, it was the first ever experiment to clearly show the quantum nature of substance. Actually, this experiment is the first experiment performed by Frank Hertz to show that the quantum nature of a substance. That is, what is the quantum nature of substance? That is, electron occupy only discrete and a quantized energy state. Okay. And furthermore, this experiment supports the Bohr's atomic model. Okay. Now we will see about the discrete and the quantized energy state. That is, if we supply energy to the atom, then it absorbs energy in the fixed manner. That is in a quanta. That is n is equal to 1, 2, 3, and furthermore 4, 5, 6. Okay. Now inside this setup, okay, we have these three voltage. Okay, there are three voltage. I will talk about this, and one filament is there. Okay, there is one filament, and there is one cathode. Okay, this cathode is given by the name called K, and this is the anode. And here there is a grid one that we called as a G1, and the voltage that we applied between the G1 and cathode is equal to BG1K. Okay, this is the variating voltage. We can vary it. I will show you where it is. Okay, BZ1K is over here. Okay, let me zoom it little bit more. I hope it will be clear. Okay, this is BZ1K. We will on this setup at first. Okay, we'll on this by connecting it into the power source, and we'll take it to the BZ1K, and we will operate this value, okay, of BZ1K. I will tell you later on how to operate. Okay, this G1 and cathode is the voltage supply between G1 and cathode K is BG1K, and the voltage supplied between G2 and cathode is BG2K. Okay, G2 means the another grid. I will talk about this later. These are the grids which have a positive charge. Okay, and the voltage supply between G2 grid and the K cathode is BG2K. And another, this is the anode. Okay, the voltage supply between anode and the G2 grid is known as voltage between G2 grid and anode, that is BG2K. Similarly, this voltage between G2 grid and cathode K, BG2K. Similarly, this voltage between G1 grid and cathode K, that is the experiment uh, diagram. Okay, just only the diagram. Now we will see about setup and why. Okay, why did we do this type of setup? And we will see. Okay, point wise I will describe this. Voltage between grid 1 and cathode K is BG1K, which is kept around 1.5 volt. That means this voltage between G1K, that is the varying voltage, but we'll keep it constant, that is we'll keep it around 1.5 volt in this experiment. How to set up? We'll take this black pointer to G1K and control this to get the value over here 1.5 volt. Okay, simple. Another, filament emits electron from cathode through a thermoionic emission. Okay, thermoionic emission, it is released. What do you mean by thermoionic emission? It is the release of electron through the heated material. I furthermore read about this. Due to the heat, okay, electron gets released. That is called a thermoionic emission. Thermo means heat. Filament emits electron from cathode through thermoionic emission. Okay, what happens is this filament emits electron from this cathode. This cathode becomes very hot, and the electron will be ejected from here. Let me write here. Okay, electron will be ejected from the cathode to the grid 1. Okay, electron will be ejected from cathode and it will move to grid 1. Okay, I'll tell you how it moves to grid 1. Now, mm, another point. Role of grid 1 is to accelerate electron and pushes forward. Okay, as I've told, these electrons are here. Okay, the role of grid 1, that is positive charge, it have positive charge. Positive charge attracts electron which have negative charge, and its role is to accelerate the electron and absorb some electron and pushes it forward. That means this can push the electron forward in the other direction. Okay, it goes forward. Now another, what is the voltage between grid 2 and cathode? That means VG2K is changed from 0 to 80 or 90 volt. Role of grid 2 is to filter the electron and pass it to anode. Okay. Um, the voltage between this grid 2 and cathode G2K is changed from 0 to 80 volt, but later, not now. After we set up the voltage between G2 and A, we will change the value for G2K. Okay. Okay. Voltage between G2 and voltage and cathode is changed from 0 to 80 or 90 volt as per our wish. The role of grid 2 is to filter the electron and pass it to anode. Okay. The role of this grid 2 is the electron which will be passed by grid 1. Okay. It helps the electron to filter and transfer it to the anode. Okay. This voltage between VG2K does this type of work. Now, small voltage is kept between anode and G2, okay, BG2A. I have told that we'll set up this voltage to a constant value, that is, we'll set up to 7.5 volt to ensure that electron pass through grid 1 and 2 are collected by anode. Okay, let's see. Whenever the electron gets passed through this G2 grid, then what happens is that electrons should go directly to the anode. For that purpose, we'll set up the voltage difference over here, that is equal to 7.5 volt. Okay, we are clear. We have supposed this voltage and this grid tries to attract electron and push forward. We have set up this voltage, okay, that such that this grid 2 filters the electron and transfer it to the anode. We have set up this voltage to catch all the electron and complete this circuit and show the reading in this anode. Okay, otherwise, oh, this is emitter which is connected in series. Okay, this is anode, this is a rod, and this shows electron, that is flow of electron current in a very minimal value. Okay. Now we'll talk here. BG1K is over here. We'll set up to, we'll take this to the left side. We'll set up here the value equal to 1.5 volt. Another BG2A is here. Okay. Middle one is G2A. We'll set up, we'll take this to middle and we'll operate this because this controls BG2A. Okay. Set up its value up to 7.5 volt and now take this black color movement on the other side, on the right hand side, and control this BG2K from 0 volt to 80 or 90 volt. We'll take this value up to 0 volt and uh, at the difference of 2 volt, okay, we'll take the reading of current reading will be shown here, voltage reading will be shown here. As we can see here voltage, and we can see here current, and there are two different um, value for filament and scanning. Okay, we'll take it to the minimum value. Okay, we'll not give more value, we'll take the very less value for this. It is compared to 0. Okay, and we can see here the minimum current will be measured by this ammeter. So we will have given the unit for current is 10 to the power minus 9 volt. Set up this up to 10 to the power minus 9 volt. Oh, ampere. Okay, current is not, never volt. It will never be a volt. It will be ampere. Okay, now we have completed. We have done setup, and why we have done setup we have seen. Okay, now working mechanism of this experiment. Now since the voltage of grid 2 and cathode from 0 to 80 volt, and observe for two different voltage um, increment, that is at 0 volt, 2 volt, 4 volt, 6 volt, 8 volt, 10 volt, 12 volt, and furthermore up to 80 volt. Okay, as the voltage increases, okay, how now whatever data we get, okay, as the voltage increases, electron gains more energy. When the energy of electron reaches the excitation energy of the gas, that is argon 11.8 volt, they causes inelastic collision, exciting the gas atom to higher energy state. Okay, I will explain this point. As the voltage increases, again we'll read, okay, electron gains more energy. As the voltage increases, electron gains more energy. When the energy of electron reaches the excitation energy of gas, okay, 11.8 volt, they causes inelastic collision, exciting the gas atom to a higher energy state. Okay, I'll explain. Okay, at first, at first I'll explain that inside this tube, there is a gas called argon gas. Okay, is here. The excitation potential of argon gas is around 11.8 volt. Okay, argon gas have an excitation potential of around 11.8 volt. Let me pick this once. Okay, I have mentioned over here. Okay, excitation potential of argon is 11.8 volt. Now what happens is, whenever you will give the value of Bg2k, okay, slowly the current starts increasing in this emitter, and as the value of Bg2k becomes, okay, near or around to 11.8 volt, the current starts to decrease. Because what happens, because the energy which the electron have will be transferred to this argon gas, and the argon gas goes to the excitation level, that is higher energy state. Okay, for the value of 11.8 volt or more. I will explain it clearly with the help of graph later, but remember the value of 11.8 volt. Okay, now that causes the inelastic collision. Okay, at this time there is the inelastic collision, exciting the gas atom to the higher energy state. At what time? That means at the time when the voltage of Bg2k becomes higher than 11.8 volt, not less. Now what happens if the voltage is less than 11.8 volt? We will see here. Before the excitation energy, that means before the voltage of 11.8 volt, there was the elastic collision between electron and gas. There was the elastic collision between electron and gas, so that there is no any lose of energy. Okay, electron do not lose any energy. There is a elastic collision which causes the increase in kinetic energy of electron, and hence the current increases. That is excitation energy. That is up to 11.8 volt, the current increases, and after 11.8 volt, there is the inelastic collision, and the current starts decreasing. Where the energy goes of that electron, it goes for the excitation of that gas to a higher energy state. Okay, again I will repeat this process. At the 0 volt, okay, we have our boundary at 11.8 volt. Okay, slowly, whenever you increase the voltage from 0 volt to 11.8 volt at 0, 2, 4, 8, 4, 6, 8, 10, up to 12, okay, up to 11.8 volt, there is no any inelastic collision. There is only elastic collision between argon gas and electron, which the grid transfers. Okay, as I have already told, there is a elastic collision. At that time, there is no any loss of energy by electron, and hence what happens is there is the elastic collision, and at the time of elastic collision, the current increases as the electron do not lose any energy, and later on, when the voltage becomes more than 11.8 volt, there is that electron energy will be taken by the gas to go to the higher energy state, and then the current level decreases to the minimum value for some time. Let us say up to 16 or 17 volt. Okay, and again it becomes elastic, and again it becomes inelastic collision. Okay, this process repeats for multiple of 11.8 volt. Okay, that means up to 11.8 volt elastic collision, it reaches current reaches to the peak, and after the 11.8 volt the current goes down due to the inelastic collision between argon gas and the electron. And similarly, up to 23.6 volt, again we'll get another peak, and again inelastic collision starts, and again up to 35.4 volt we'll get a peak, and again inelastic collision starts. Okay, and it goes on further for the multiple of 11.8 volt, because 11.8 volt is the excitation energy level for argon gas. Okay, now we'll get this type of result between voltage and current. If we increase the voltage from 0 volt, the current level will be will get a several peak at the several different time of voltage. So result, this is our result: the appearance of peak and valleys in the anode current. Okay, anode current means where do we get a current? We get a current over here. Okay, this is the current between anode and this one. Okay, G2A. This is the voltage, and in this circuit, overall circuit will get this current. Okay, this current have a several different peaks at the several different time of voltage. The appearance of peaks and valleys in anode current as a function of accelerating voltage. Due to the accelerating voltage, we'll get a current at the several different peaks. This indicates that there is a discrete or quantized nature of atomic energy level. Okay, the presence of peaks show that there are a discrete or quantized energy level. Okay, as I've talked before, the main function of this experiment is to show the quantum nature of substance, that is, electron occupy only discrete and a quantized energy state. Okay, and this experiment supports Bohr's formula because of this peak. Okay, and furthermore I will show my observation table. Okay, only this little bit. Filament voltage is kept up to 2.6 volt. Okay, we'll give it to a minimum position. Okay, we'll not measure this. Okay, we'll give a minimum value: bg1k 1.5 volt, bg2k 7.5 volt, and bg2k. Okay, bg2a, this is a up to anode. Okay, bg2k, that is equal to 0.4 volt, and will increase from here to up to 80 or 90 volt. Current multiplier we have set 10 to the power minus 9 ampere. Current multiplier we have set up to 10 to the power minus 9 ampere. Whatever current we get, we have a unit multiply by 10 to the power minus 9 ampere. Okay, we have a current value up to 10 to the power minus 9 ampere, and For a different voltage, we'll see the value of current. We can see up to 10 volt only. We have seen little bit current, 0.1 into 10 to the power minus 9 ampere. And after some time, it goes on increasing. Okay. I have shown data only up to 10 volt, but up to 60 or 80 or 90 volt. Okay. We can analyze with the help of this graph, whatever data we have got in the value of current. Okay. So the video becomes a little bit lengthy because it is informative. I hope you enjoy it. And if you have any type of question, leave it in the comment section. We'll meet again. Bye-bye.